Afternoon, Eamon Darcy is my name. I'm the founder and director of QEQA, the Quantum Education Centre of West Australia. And QEQA's only really two major objectives in life. Firstly, to bring quantum physics and specifically quantum computing, which is going to change society completely in 5 to 10 years, to the general public. And secondly, to develop intellectual children. I often get parents come up to me saying that their daughter or their son is very clever, very gifted. They never say they're very intellectual. And that's simply because the child is not confronted with intellectual issues in an intellectual way. Our tagline at QEQA is, if it's not taught, you're not going to learn it. So nothing annoys me more than when a 5-year-old looks at the beautiful Perth night sky with all those beautiful stars and asks so many questions about galaxies and solar systems and black hole and dark matter and dark energy. And the best we can say is, oh, well, look, go to university, get a degree in physics, and then major in astronomy or cosmology. That's no good to a 5-year-old. So moving straight on, today I'm going to talk about Einstein's special theory of relativity, which, like all matters in physics, sounds a lot more complicated than it is. It was very difficult to come up with it in the first place, but it's not difficult to understand what's happening. I explain it to my 6-year-old granddaughter by telling her that, according to strictly scientific principles, I could make it so that she's 100 years older than me. So after she stops crying, getting upset, we talk about it, and yeah, it's amazing that is true. And it's because Einstein taught us that space and time are related, and the faster you go through space, the slower you go through time. Now, so I'm going to focus on time dilation, which is precisely that. So I'm going to, there's two things you need to understand. One is a thing called an inertial frame of reference. Now, it's not difficult. That just means that there's no such thing as absolute speed. Your speed is only relative to somebody else's speed. And that's actually what we call frame of reference. Inertial frame of reference just means a constant speed. If you accelerate and decelerate, then Einstein's special theory of relativity doesn't work. You need to look at his general theory of relativity. But for today, we'll just talk about an inertial speed, so it's a constant speed, and how time varies according to that. The second thing you need to know is that time, the speed of light is constant. 300 million meters a second, and it never changes, no matter what frame of reference you're in. And that's very strange. So, with no further ado, let me explain to you time dilation. Einstein taught us that speed could only be measured with respect to other frames of reference. And we see this in everyday life. The animation I'm going to show you in a few seconds shows that when we're in a car going at 90 kilometers an hour and we're overtaken by a car going at 100 kilometers an hour, we see that car slowly inching past us at 10 kilometers an hour. To us, in our frame of reference, it's not going at 100 kilometers an hour. It's going at 10 kilometers an hour. But if you're a bystander at the side of the freeway watching both cars, you would see our car going at 90 and the other car at 100. So it all depends on your frame of reference. And in your own frame of reference, you are always still. We're in the green car going at 90 and the red car's going at 100 kilometers an hour. But to us, in our frame of reference, it's only going at 10 kilometers an hour. If you happen to be an observer watching both cars, you can see that the green car's going at 90 and the red at 100. But light does not work this way, Einstein taught us. Light is always 300 million meters a second, whether you're standing still, in a plane, or in a spaceship virtually going at the speed of light. You would still only see light at 300 million meters per second, never faster or slower. So what can we work out from this? Okay, let us imagine that we're the lady in purple, we're in a carriage moving along a track, and we shine a light from our torch to the mirror. And W is the distance from our torch to the mirror. So time, how long does it take for that light to get to and fro the mirror from us? It's 2W divided by the speed of light, which is c. And we'll call ourselves T stationary because we're inside the carriage. Okay, let's introduce a new frame of reference, which is the lady in orange. She's a bystander watching the train go by. And how does she see the light move? Because the train is moving, she sees the lights moving along a triangular movement. Now we need to include Pythagoras' theorem. Okay, so V is the speed of the train and C is the speed of light. And the mathematics don't matter too much at this stage, but simply using Pythagoras' theorem, we can test that W equals the square root of C squared minus V squared. Very easy to prove. So again, we don't need to get caught up into the maths. It's some very basic maths that prove beyond a doubt that time for the moving object, time passes more slowly. So let us summarize. To the lady in purple inside the carriage, the light is merely going up and down the perpendicular. To the observer, the bystander, the lady in orange, the light is traveling along a triangular path. It's traveling along the hypotenuse. It is going further. Something has to give because the light, it travels always at the same speed, but it's going a greater distance. And the thing that has to change is time. Time goes slower for the inside the moving body. I hope you've enjoyed this video. Please visit our website, www.quechua.org.au, and follow us on YouTube and Twitter. Thank you.